Debunking the green NFV myth, an assessment of the virtualization sustainability in radio access networks. With the fifth generation of mobile networks, new classes of vertical applications and services will be enabled. Their extreme low latency requirements will eventually challenge telecom providers to satisfy growing demands in a sustainable way, as the increased amount of data traversing the network will be reflected in higher costs to build, to operate, and to upgrade mobile networks. Network functions virtualization is considered very relevant to overcome these challenges. In fact, the 5G service-based architecture has the core functionalities designed as highly pluggable virtualized network functions. By allocating VNFs on demand, individual instances can be horizontally scaled according to the current load and the latency requirement of next-generation mobile applications. This is believed to both reduce power consumption and simplify upgrades and maintenance of the infrastructure because of the virtualized environment. However, there are no clear figures supporting these claims, so it is debatable whether NFV by itself would improve energy efficiency, performance, or operating and capital expenses. So, to seek some clarification, in this paper we have examined the virtualization of the radio access network to try breaking down the power consumption and costs expectable when deploying NFV technologies in real networks. We have focused in particular on CRAN technologies. The evaluation is based on real publicly available datasets from an Italian mobile operator, Telecom Italia Mobile, and on datasheets from both commercial devices and pools of VNFs under different deployment scenarios. Although the concept of CRAN is almost 10 years old now, it has recently gained momentum thanks to the maturity level of some of its enabling paradigms, like cloudification and NFV. In fact, with the resources flexibly allocated according to the current demand and executed on general-purpose hardware for base stations, costs can be reduced both when planning and deploying an infrastructure, and then when upgrading. Now, CRAN is even more relevant considering 5G. In fact, instead of a monolithic architecture, 5G has been conceived from the start to be service-based, with functions deployed as VNFs running in virtual machines in cloud computing infrastructures. Both access and core functions at data and control plane can be centralized or distributed. In addition, the adoption of CRAN could help with the transition from 4 to 5G, because 5G is designed to support multiple access technologies. So, in an initial stage, it could be integrated with LLTA RAN for a quicker enablement of the new 5G services and business models. We consider the CRAN deployment over a reference metropolitan area that includes Milan, Italy, and neighboring cities, the area that is shown on the map. The map also shows the LTE node Bs deployed by Telecom Italia Mobile over the reference area. This information is accessible in the OpenCell ID database. We consider the Internet traffic activity over the area for the Telecom Italia Mobile customers from the publicly available Open Big Data initiative. Since the entries of the dataset reported the level of interaction of the users with the mobile network, we have multiplied them by random traffic rates in line with the Cisco Mobile Visual Networking Index, so that we can work with rates. We have compared the traffic activity on a working day and a holiday. You can see the heat maps representing the distribution of users on December the 6th and December 25th. So, to characterize the traffic volume for each node B over the selected days, we have run an emulation assigning the user traffic from the Open Big Data initiative to the closest node B. Constraints on the maximum allowed traffic volume ensure that if the closest node B capacity is nearly saturated, the second closest is selected and so on. Since a single BBU pool placed in the center of the reference area allows fulfilling the subframe processing delay constraints, regardless of the BBU technology, we can consider spectral efficiency, fiber connections, and front-haul transmission solutions to be the same for all test cases. In particular, we consider two deployments, one using commercial products, dubbed CBBU, and one using virtual server-based BBUs, which is called VBBU. Information on the CBBU comes from product datasheets. To characterize the VBBU, we have used the architecture and related performance models from a paper by Yunis and colleagues that is based on open-air interface. The goal of our evaluation is to compare the BBU power consumption of commercial devices and pools of VNFs. We have evaluated how power consumption changes throughout the day and between working days and holidays for the CBBU and the VBBU cases described in the previous slide. Since we consider a single centralized BBU pool for both cases, we only account for the consumption ascribable to the devices. For the CBBU, one module is deployed for each node B in the reference area and is kept constantly powered on. While for the VBBU, we consider a number of active servers, varying according to the load as indicated in the UNIS paper, and of switches computed by using the K-area factory topology. This graph shows the daily trends for the two cases obtained on the 6th and 25th of December. Since the devices deployed for the CBBU case are always active, there is only one line for both days, and it shows a constant value throughout the different times of the day. Thanks to the power saving mechanisms available in general-purpose processors, the VBBU case presents significant differences between the working day and the holiday, with variations up to 70% between the 2 days and 20% throughout each day. VBBU has a higher level of proportionality with the incoming traffic load and provides better results when the traffic is low. Notice what happens between midnight and 2:30 a.m. However, consumptions are significantly higher with respect to the commercial deployment. While NFV has been trending for several years now, actual implementations are still in prototypical state, and of course a comparison with a mature commercial product is clearly not a fair one. There is still room for improvement. Among the most promising solutions, there is the decomposition of specific PNFs into subtasks to be executed in parallel to fully exploit the performance potentials of multi-core processors. Also, the consolidation policies typically applied within data centers can be used to tune the resources assigned to VNFs. But unfortunately, these approaches generally cause unfavorable trade-offs towards either power consumption or performance. So at least with the current generation of processors, it is unlikely that NFV would be able to measure up to commercial products. The flexibility and scalability promoted by NFV on general-purpose servers can be used alongside specialized hardware solutions to reap the benefits of both technologies. For example, NFV could be used in the presence of lower traffic loads, and then commercial products where and when demands are higher. We have explored this heterogeneous approach by taking again the results from the evaluation I've just shown to identify the average traffic processed by each node B in one day. If the traffic level is low enough to fall in the range in which the VBBU consumes less energy than the CBBU, the range in the red box, it is processed by the VBBU pool, otherwise the node B is paired with the commercial BBUs. You can see the obtained assignment on the map, with the deployed node Bs paired to CBBU in red and those paired with the VBBU in blue. We have compared the power consumption obtained for the CBBU and for the heterogeneous use of commercial and virtual BBUs, which has been called HBBU. We considered the data from December the 6th. Results from the CBBU are the same as before. In the HBBU case, incoming traffic to the node Bs that present a low average load is managed by virtual BBU instances. As a result, the consumption ascribable to them is significantly reduced. Keeping the hosting servers powered off most of the time allows for energy savings that peak up to 20% and scale with the traffic load. We have also drawn some very high-level considerations on the operating and capital expenses. Centralization by itself can already reduce deployment costs and improve power usage effectiveness with respect to a traditional run. However, as such reductions can be achieved only by extending the coverage area as much as possible, they may be counterbalanced by space-related and hardware costs. The graph you see reports an estimate on OPEX and CAPEX over a year for the three task cases. Since a complete analysis of the total cost of ownership is out of our scope, we have considered only the costs ascribable to the hardware performing run operations. So OPEX includes the cost of energy consumed by the hardware and not operations and maintenance, staff, or rent, and that's why it's so much lower than CAPEX. Costs related to the VBBU are significantly higher than the other two cases, while HBBU is basically the same as CBBU. This is actually extremely promising because for the same cost of commercial hardware devoted to one single task, HBBU provides a deployment that is flexible enough to host other applications aside from RAN, and that can be extended seamlessly both for scalability reasons and to foster new generations of network and computing resources. The coming of 5G will increase the amount of data traversing the network and increase as a consequence the cost to build, operate, and upgrade mobile networks. Since the adoption of virtualization paradigms is considered as a viable way to fulfill the requirements of next-generation applications in a sustainable way, this paper has tried to quantitatively assess this claim by comparing the BBU power consumption obtained using commercial devices or pools of VNFs. Results have shown that the usage of the virtualized BBU pool gives better results than commercial products when the traffic is low, but average consumptions are around 250% higher, and OPEX and CAPEX are above 66% higher. On the other hand, the deployment of VNFs alongside specialized hardware provides energy savings up to 20% and costs in line with the ones of dedicated hardware deployments, showing that remarkable benefits can be obtained by exploiting the scalability of software solutions in the presence of lower traffic loads, and then switch to commercial products when demands are higher. Thank you for your attention. If you have any questions, do not hesitate to send